Now since last 2-3 classes we have been discussing about the 2D COSY. That is the most important experiment for any chemist. If you have to make the assignment of all your molecules, if you synthesize a molecule, characterize it, take the 1D NMR spectrum, if the molecule is complex and little bigger, there will be a lot of peaks. And how do you make the assignment of unambiguous assignment if you have to make? COSY is the best way. And we took several examples, how a COSY works, what it does for a coupled spin, uncoupled spins, everything we discussed. And I said always one dimensional spectrum of a COSY appears on the diagonal. Take the spectrum of COSY spectrum of any molecule, sit on the diagonal, come vertically down, go horizontally and complete a square. Then this diagonal peak and this diagonal peaks are coupled partners. Wherever you get the cross peaks, those diagonal peaks are the protons which have different chemical shifts. They give rise to cross peak. Like that, from that diagonal you can find out the other cross peak if it is there. So you can continue like that step by step manner and make the assignment for all the peaks in the given molecule. So COSY is the simplest experiment to identify the immediate coupled partners. So with that we will take another 1 or 2 simple examples, then go to a complex molecule. And today we will also see some examples of little different types of COSY experiment if there is time. So I will take another 1 or 2 example where complexity is there. How do you make an assignment? Now that you have become very confident already, I can go a little faster here to make the assignment of this one. Okay, we will start the another molecule here. This is COSY spectrum of 6-SLL benzoate. This is the structure of this molecule. And confidently I would always say this is CA3, start with CA3, proton 11. And then come down, you complete this has to be proton 10. And proton 10 gives rise to a cross peak here. So this has to be proton 9. And here proton 9 has a cross peak, there is a multiplicity pattern here. You can see 2 groups here. That proton 9 is also giving cross peaks, it can give to these etc. So that could be for a proton 8. From proton 8 you have a cross peak to 2 things. One for S, one for 10, proton 8 to 10 also is there. And also it is giving rise to cross peak to 7. It can give rise to cross peak to 7. See, from proton 8 go here, complete this square, and this is 7. And of course there is another diagonal here. What is the diagonal? If you carefully see, you don't get confused. We will see with start with 10, 11, you will get 10, 10 to 9, 9 to 8, 8 to 7. You complete this square. And 7 we can complete this square. From 7 diagonal come down, you hit diagonal and complete this square. So this has to be proton 6. So that completely analyzes this bunch. We can make the safe assignment without any difficulty. But what is left over? Left over is only phenyl part. In the phenyl group, of course, 1, 2 and 3 I can simply make the assignment based on the intensity pattern. This and this proton are equivalent. These two are equivalent, gives double the intensity, and this is a single proton, paraproton, half the intensity. So very easily you can identify this. I did not mark it there, that's fine. But you go to the another molecule like this, very simple, 500 MHz COSY spectrum of a molecule like this. Here we have two protons. You have to assign which is the proton in which you are confident. Obviously I look at the proton 2 here. This can couple to only one of the protons and become a doublet, immediate coupled partner. I would say this is proton 2. And then go here horizontally, you will see proton 3. See here, proton 3. From proton 3 I come here, go vertically up, and then I will complete this square. This is 2 and 3. Complete this square, this is 3 and 4. From 4 I can come here. Of course there is a bunch here, 4 and 5 cross peaks are there but are unresolved. From 5 I come here, complete this, I complete this square. 5 is coupled to 6. But 6 has 2 protons. 5 is also coupled to 6 prime. There are 2 protons here. Both are 2 bond coupling or 3 bond coupling with proton. This for H5. So we will have 2 cross peaks here. This and this. So if this is 6, other is 6 prime. So you can continue completely as make the assignment. Very simple. Which is 6 and which is 6 prime? You have to use the knowledge of coupling constants. Alright. So if there is a dimer like this, for a molecule like this, there are 2 dimers. A dimer of 2 molecules here and here. How do I assign? See, there are assignments have been very easily made. Look at this molecule, go vertically up, they are all red lines, and it forms one spin system systematically, which all correspond to one of them. And all other one for this molecule B, start with one of them B, come here, and then of course go here like that. You can assign for other molecule. Even though it's a dimer, it's a bigger molecule, very slight difference in the chemical shifts are there in each of the cross peaks. Very easily you can make the assignment. So I hope by now you have already got the idea how to go ahead and make the assignment. I will take the assignment of a molecule like this, a sugar-like molecule. It's a glucoside. Always, if you want to analyze the molecules of sugars, please remember most of the time, it's an anomeric proton comes downfield. It is always between 4 to 5 or 6 ppm. So you look at the anomeric proton, and that is the only proton which can couple with another proton which gives rise to a doublet. What is that proton here? If you look at it in this molecule, this is a doublet coming in the region of around 4.4. Safely I would say that is anomeric proton H1. You have to use the chemistry logic now. I use that as a H1, anomeric proton, and using that anomeric proton I will complete the square. That must be proton H2. Obviously this is proton H2. H1 is coupled to H2. So very easily you can make. See, please remember I am taking this example to show you that in the case of sugars and others, always start with anomeric proton. That makes your job simpler to analyze. And then if this region is expanded here, this region, you will see what is going to happen. The entire region up to this is expanded. And you can see what will happen. We already know this is H2. From anomeric proton we got this. From H2 go here, come here, complete a square. But why this central peak is missing? Okay, this is the antiphase character. As a consequence, what happened instead of 1:2:1 is 1:-, -101 intensity is coming. So that is, it can happen sometimes. The central peak disappear like that. Okay, doesn't matter. From this you start, complete the square. So that has to be proton H3. From proton H3, again go down, go horizontal, come down like this, complete this square. Then this has to be H4. We started with H1 in the previous slide. H2, H3, H4. Then from H4 here, you can continue like this and complete this square. So this has to be H5. Very easily you can make the assignment. Now H6 and other things are here. Separately, up to this was expanded, we could get up to H5. Now H5 is known. From H5, what are the two possibilities you can think of? H5 is coupled to two protons here. H6 has two protons. So come here and complete this one. This one H6A, another one H6B. Why I said H6A and H6? Axial and equatorial you have to assign based on the coupling strength. Always remember, axial coupling is larger, axial equatorial coupling is smaller than that, and equatorial coupling is even smaller than that. So you have to look at the multiplicity pattern and see which is larger coupling. So from that you can know whether it is axial proton or equatorial proton, and then you can make the assignment. So that is the usual way we have to start doing it. And we will go to the 2D spectrum of a protected peptide like this, and very easy in a protected molecule. Again start with anomeric proton, complete the square, keep on going like this. One with I go here and then complete and go to 2. I am not completing the square, I assume that you know by now. 2 to 3, 3 to 4, 4 to 5 or 6, we do not know, whatever it is. Both 5 and 6 are indistinguishable, they are overlapped here. Fine. Also there is a pyramid base group is here. With that we can take and make the assignment here with a pyramid base group. That is also there. Pyramid base group is giving rise to cross peak. This is the anomeric proton, and of course this is the pyrimidine base group is there. With that base group, with the anomeric proton here, you can make the assignment for these two protons, aromatic protons. So this is how we can start making this thing. Some complications will come at times. I will take the example of the proton analysis of phenyl groups. I have deliberately taken this molecule. Remember, here there are 4 protons. Here there are 3 protons. From the multiplicity pattern I can tell you this has to be a doublet of doublet, one meta coupling and a para coupling. This has an ortho coupling and a meta coupling, doublet of doublet. This is also similar. All those patterns you have understood already. You have discussed quite a bit about the multiplicity pattern of the phenyl protons. Okay, we will start with this. I will say this is one spin system, this is another spin system. There are two different spin systems. These two protons are numbered, these three protons 1, 2 and 3 forms one spin system. This 5, 6, 7, 8 forms another spin system. Now analysis of this one is very easy from the COSY. Start with this H1. Why I will say the H1? This is the only proton, it can have metacoupling and a paracoupling. If it is not resolved, it is a doublet or doublet of doublet, very weak the separation, very small separation is there, you can find out. That has to be H1. And from H1, I will start with this and say this must be H3, because H3 can have a first orthocoupling large and then each lane is going to be a doublet of a doublet because of this, that is H3. And H3 is going to give rise to a coupling to other one, that has to be H4, this has to be H4. That is a doublet. It not a triplet, but you know this one doublet is here. Other part of the doublet from other one is overlapped here from other phenyl ring. See, there is a overlap here. So you can see here this peak correspond to this doublet and this peak correspond to this doublet. You can make the assignment very precisely here. Okay, we will start with this one. I would say this is proton 8 or 5, does not matter. There is a confusion. I will start with proton 5. Proton 5 will couple to this one and become proton 3, proton 6. And proton 6 has to be two triplets. Okay, because this is doublet of doublet and orthocouplings are nearly equal, it appears like a triplet. And then further split because of the metacoupling, it is triplet of doublets here. Same way for this proton. From 6 you will get to 7 and from 7 you go to 8. In this type of phenyl groups, very easy to assign using the COSY. That is why I took this example. But there is one ambiguity here, whether this proton is H5 or H8, because both of them will give doublets. See, both of them will have identical pattern. This is doublet, doublet of doublet of doublet. Both of them will give 8 ring pattern. If unresolved large coupling is there, a doublet and doublet of doublet. So which is which? Whether this is proton 5 or this is proton 8, I do not know. For that, there is an ambiguity of the assignment of spin system. Whether this is the pattern you have to assign or this is the pattern you have to assign, we do not know. For that, what we do is we resort to an experiment called NOE, separate NOE experiment, which how we can assign by separately irradiating one of them. So when I do the NOE, I will take the example of this and I am going to discuss at that time. So there is no point in going for that now, because that will be a separate this thing we have to discuss by doing NOE. But instead of that, what I am going to do is I will start analyzing the 2D COSY spectrum of a glucose. This is where another important thing. See that molecule, I will come back when I do the NOC, because I have not discussed NOC yet. When I discuss NOC, there are two ways of doing NOC, steady state NOE and transient NOE. And steady state is a simple one dimensional difference NOE. That is why I did not explain this to you, because when I explain NOE, you know that. I will come back and do that. In the meantime, we will go to the 2D COSY spectrum of D-glucose. See, glucose exists in two forms. Conventional glucose what we take, it has got alpha and beta form, 64% beta and 36% is alpha. That is the mixture, it exists in two forms. And this is the alpha important thing. Before you go to the analysis of the spectrum, you should know what is the coupling. As I told you, axial couplings in sugars are larger than axial equatorial. Then equatorial is much smaller. So always this is larger, this is small next to that, and this is smaller than both. This information is needed, and of course geminal coupling like this is quite large. Why I say this is needed? When we have ambiguity in the assignment of, let us say, groups like 6 and 6 prime like this, or 5 and 5 prime, which is the one which you have to consider? Then both gives rise to cross peak, but we use knowledge of coupling also at that time. So this is the 1D spectrum of alpha and beta D-glucose together. Look at this, is always two anomeric protons comes to the downfield. I told you this is anomeric proton of beta, and alpha D-glucose also structure I have not written. This is anomeric proton is coming, and this is the carbon 13 spectrum. Let us will analyze the carbon 13 spectrum. There is no need to do now because carbon 13 we discussed. One important thing is this type of sugar molecules everything is recorded in water which comes at 4.786 ppm. What happens is we record the spectrum in D2O. D2O exchanges all OHs present in the molecule. They all come around some water near water peak or get exchanged with water. You will not see OHs peaks. So, only we will have to worry about anomeric proton and other protons. Generally OHs are exchanged in D2O if you record in D2O. So, but two anomeric peaks are important. As I told you, it always comes between 4.5 to 5.5 or less than 6 ppm. And look at the peak's intensity. I told you 36 is the percentage of mixture present in water. But when you measure the intensity of the peaks in the NMR spectrum, almost same ratio we got. 64 intensity. Look at the anomeric proton spectrum here. This is the one, and this, if you take the ratio, this is larger than this one. This is 66, this is 34. So, clearly I would clearly say this because of the intensity, this corresponds to beta glucose. So, anomeric proton you look from the anomeric proton peak, start making the assignment. So, anomeric proton, if you know, we can just based on the J values itself we can assign. Why? Because remember in the case of the alpha glucose, the doublet is axial equatorial coupling. Axial equatorial coupling is small, whereas in beta glucose it is axial coupling, that is quite large. I will show you in the structure here. See, look at in NMR spectrum, look at the separation quite large. So, obviously that, as I told you, has to be beta glucose. Using the coupling strength of anomeric protons splitting pattern, which coupling of large value compared to alpha, I can make the assignment. So, I will start with this. This is beta, this is alpha. These are anomeric protons. Further, we can start with the COSY pattern. How do we assign the COSY spectrum of this? We already start with, you know that, start with the anomeric proton. See, anomeric proton, one which has a small coupling is alpha. We complete this. So, if this is alpha, this is 2. If this is anomeric proton 1, this has to be 2. Now, the structure of both of them is given. If you consider this anomeric proton, this has a axial coupling, whereas this one has a axial equatorial coupling. So, that is a problem. That is why this coupling is much smaller, whereas beta has larger coupling. I can make this assignment. Alpha, if I know 1, I know 2 very easily. I can make the assignment. Similarly, for beta anomeric proton, I complete this square. I know then this is beta, this is 1 of beta, this is 2 of beta. So, two protons, alpha anomeric proton 1 and proton 2 from alpha. Similarly, anomeric proton 1 and 2 of beta, we can make the assignment. I use the knowledge of chemical shift anomeric proton and the coupling separation. That is why I said you should remember axial coupling is larger than axial equatorial. This is the important concept you have to use while making the assignment of all these things. So, now we know what is alpha 2, complete with 2, go here, complete 3 and go down, go completely, and this is 4, and then complete this square, this becomes 5, and from this you have 6 and then 6 alpha and beta. Here the problem comes, 6 alpha and beta. If you go for the structure, why it is 6 alpha and beta, which is alpha and which is beta? How do I know which is alpha and which is beta? This is where knowledge of coupling we have to use, looking at the splitting pattern. And also generally it is known that one of this equatorial proton, it comes here, axial proton comes here. That is, there is always some chemical shift difference of 0.3 to 0.4 ppm. All right. So, similarly beta glucose we can do. We start with 2, complete the square, this is 3, and then this is 4, 5, 6 alpha and beta. So, all the complete assignment of alpha and beta glucose can be done. This is a complete assignment of glucose we have done. This is where you can see the expansion. Beta, which is axial coupling, is larger, and this is smaller alpha. We use that as a starting point and use the COSY to make the assignment. Okay, with this most of the assignments we have done, and what I am going to do is I will discuss something more about the different aspects of COSY experiments and what are its limitations. We have discussed about the COSY so far, but what are its limitations? Okay, we are comfortable by now. So many molecules start from simple molecule, mixture of molecule like glucose, and varieties of things. And I gave you idea where do you start in sugar molecules or in aromatic protons. Aromatic groups are there. Where is the comfortable point for you to start? That's what I wanted to tell you. Let us see what are the limitations of COSY experiment. First thing is the polarization transfer between the coupled protons and depends upon the strength. If the coupling is larger, cross peak will become stronger. If the coupling strength is very weak coupling is there, you will not be able to get the cross peak. Even if you get cross peak, it may be very weak in intensity. And all the 2D NMR peaks have a fine structure and they contribute to diagonal and cross peak. There will be coupling will be there. So each peak, as I told you in the two spin, each diagonal peak will be 4 with square pattern. Each cross peak will be 4 with square pattern. But in all these bigger molecules, the resolution is not there. We didn't see. But in principle, there are fine structures. And a cross peak contains both positive and negative signal, whereas diagonal peak contains only the positive signal. That's what we also discussed. I discussed about the pattern of the diagonal peak and cross peak. But when there are signals are broad, unresolved, because of negative and positive signal close by, they cancel out. As a consequence, there is a drawback. Sometimes you will not see the cross peak at all in COSY. When you don't see cross peak, it may be because there are two antiphase pattern peaks, antiphase peaks are there close by, so that will get cancelled out and you will not see. And diagonals are in phase because it is a huge peak. It will mask the peaks close to it, some of the cross peaks very close to it. And sometimes diagonal peaks very large, it gives rise to tiles. Okay. So another thing, whenever you record a spectrum, what is the line shape you are going to get? Of course, 1D spectrum has to be like this, very clear. We have to do the line shape analysis to get a sharp peak. We usually take CSCL3 and measure the peak of height of the satellite, and then that is at 1.1% and half of the satellite height, and then we measure the height of this. Very easily we can measure and get the line shape. Line shape analysis is done. This I have discussed extensively in one of the courses. Since I am not discussing this course focus is different, so I am not telling that. But there are 3 different types of pattern you are going to get, peak shapes in the COSY or any 2D NMR. One is pure absorption line shape like this. It is like a star picture. Other one pure dispersion like this. And this is phase twisted line shape. These are the 3 different types of spectrum depending upon the type of experiment you do. That is whether you are doing the magnitude type experiment or phase sensitive experiment, or whether you are processing it to get the double absorption line shape. That's what matters. So always the spectra are represented in 2 ways. 2D spectra are represented 2 ways. One is phase sensitive mode, other is magnitude mode. Magnitude mode means there is no phase information, that is last. No phase information, everything is discorded. Phase sensitive is always important. Okay, so and magnitude mode is not good for high resolution because you cannot distinguish between dispersive and absorptive peak, they are mixed up. Phase sensitive on the other hand is very good. You have line shapes of absorption and dispersion, both are separated out. And generally absorption mode is preferred for high resolution. That is what we do. Look at the COSY spectrum. Cross peaks, if you do the magnitude mode COSY, you get a star like pattern like this. Usually you should get sharp peaks with a double absorption, means very sharp peaks, but we get star like pattern. This is because of mixture of absorption and dispersion like this. This is a magnitude COSY, record in the magnitude mode, not phase sensitive mode. Okay. In both F1 and F2 dimensions, sometimes we have, of course, one important thing, Fourier transformation when you do, you have real component and imaginary component, each dimension. In both dimensions if you do, you have 2 real, 2 imaginary. There are 4 possible combinations then, real, imaginary real imaginary and imaginary. There are 4 possible combinations. Accordingly, we have 4 different types of line shapes. For example, look at this is one dimensional imaginary, other dimension real. You have both the dimension imaginary. Here real and imaginary, and both are real. And look at it, this is a sharp peak. Look at this is very broad, imaginary. This is one side broad, other side is sharp. But this is what we have to consider. Always double absorption mode gives a better resolution. Please remember, when you want to record the spectrum of COSY and others, always do the phase sensitivity detection with a double absorption mode. The data has to be pure double absorption mode line shape. This is the double absorption mode line shape. Lines are very sharp and this is the contour plot. This is the stack plot like this. So, double absorption mode is always preferred for better resolution. That you should know. And there are several variants of the COSY experiment. COSY can be of several types. One is DQF COSY. The double quantum filtered COSY is something where advantage is, lot of you will remove all the peaks, cross peaks which are masked by the diagonal, etc. And it is very easily you can get positive negative signals, very easily you can resolve it. And singlets like reference, solvent peaks, they all get suppressed. Because we take the magnetization to double quantum pathway and then bring it back for the detection. This is the way we have to select the double quantum pathway. Similar to COSY, only thing is second 90-degree pulse generates multiple quantum coherence which is not detected by the receiver. So, and the double quantum is always converted to single quantum. As I told you, anything selection rule, anything other than delta m plus or minus 1 is not detectable. There are multiple quantum. We always detect single quantum NMR. I told you plus or minus 1 is single quantum, that is what we detect. So, by you do some process of selection of this double quantum, you can pass it through that by using phase cycling and then convert into single quantum. This is the way we do this by applying a 180 pulse. And how do you do the coherence pathway selection? And we have to apply different pulses. This is a more detail, you don't worry about it. But DQF COSY experiment with coherence phosphate selection is always like this. It is a simple experiment, similar to COSY, but little modification is there. You can see here after 90 pulse T1, this is not 90, lot of modification is there, and also with a gradient selection. There is a phase. Previously I said in the coherence transfer pathway you can use the phase, different phases you can do by this is phase selection. Okay. Alternately you can use gradient. Phase cycling can be done or gradients. So, generally in the phase cycling version DQF COSY both the coherence pathways are retained. In the gradient only one coherence pathway is retained. There are two different coherence pathway always. It can go here, come back to one, come back and come to here. There are two coherent pathways. In the phase cycled version of DQF COSY both are retained, whereas in the gradient version only one is retained. Obviously that tells you the sensitivity of this is less compared to coherence phase cycle selected way. Okay. And the diagonal and cross peaks of both phase antiphase double absorption mode line shape, and they are not affected by double quantum filtration. Advantage is whatever the tailing we get, severe tailing at the diagonal, they are all removed. So, it gives a better quality spectrum. DQ double quantum filtered COSY gives you better quality spectrum. The singlets from uncoupled protons, solvents, reference, all are suppressed. You won't see it at all. There is a biggest advantage of that. So, major advantage of DQF COSY is removal of dispersive component of the diagonal peaks. As a consequence, this is the spectrum which is much better. A simple typical example of a DQF COSY spectrum. Look at this one, diagonal, both positive negative peaks are present. Here both are positive negative. Earlier case, in the case of COSY, both were positive peaks at both the dimensions. Here they were antiphase doublets here. In the case of conventional COSY, you see here positive negative. Both diagonal cross peaks are antiphase absorptive. In the conventional COSY, only cross peaks are antiphase, diagonal are in phase. But here it is different and they are double absorptive, gives better resolution. I told you representation of the cross peak in the COSY, always double absorption mode is preferred. And the typical DQF COSY spectrum, always there are no diagonal peaks will mask the cross peaks. If there are cross peaks nearby here, they will not be masked. Whereas remember in the COSY, huge peaks will be there because both are in phase, diagonal peaks, and that will mask the peaks nearby. Sometimes you will not be able to identify. Here is a comparison. Look at the COSY spectrum of this molecule. It is a pentapeptide. Look at this molecule. Look at the COSY spectrum. How trails are there. Peaks nearby, you will not be able to see. They are all masked. It's a clumsy spectrum, very, not good at all. On the other hand, look at the decay of COSY spectrum here. Fantastic, it's a double absorptive line shape, and both the side, phase, you can see antiphase character is there for all the cross peaks and diagonal peaks. Look at the resolution here. Look at the resolution here. So both give the same information. There is no difference at all. But look at the better quality of the spectrum. So always a suggestion I tell for the participants, don't ever do COSY spectrum. Always do decay of COSY. That gives you a better spectrum. COSY spectrum like this is very clumsy and you will not be able to get the good resolution. Okay. This is a simple example to show how the decay of COSY spectrum is obtained on a molecule like this. See, look at this molecule. This is the molecule structure, and you can see one peak, another peak, two spin systems are easily identified, and this is the structure of the molecule. You can clearly see the structure of the molecule. From the structure you can make out there are one group here and one group here, that is all. But look at the resolution here, diagonal and cross peak. Fantastic resolution you are going to get compared to cross peak. So peaks near the diagonals are also very well resolved. This is the advantage of decay of COSY. And other variant of the COSY is about COSY 45 is there, COSY 9 and delayed COSY is there. And of course, let me see how much is there. I think there is a little bit is there. I will finish it so that tomorrow I can start with another 1 minute. I will finish this one. Okay, COSY 45 is the simplest experiment. Instead of 90 degree here we use the 45 degree. What is the advantage of it? Intensity of the cross peak near the diagonal becomes weaker and the diagonal becomes narrow. But another thing is cross peaks appears tilted like this, and the direction of the tilting gives me relative signs of the coupling. Instead of 90 degree, if you use second pulse as 45 degree, not 45, any angle. Soft COSY we call it, we can use 20 degree, 30 degree, 50 degree, whatever the angle you want. But then what will happen is, compared to this COSY 90, this COSY 45, some of the peaks are missing and some of the peaks appear tilted. And the direction of tilting gives you the sign of the coupling. Usually if you look at some of the molecules, vicinal couplings are usually positive and geminal couplings are negative. And if you want to find out the relative sign of that, low flip angle COSY, where the second pulse using 45 degrees better. You can also have a long range COSY, also called delayed COSY. What we do is, after the T1, after the 90 pulse, before T1 you apply one pulse, one delay here, and after another pulse you give another delay. Additional fixed delay is there given before and after the second pulse. This will enhance the resolution. But the total evolution time is constant. That is always retained to get the better digital resolution. And then what will happen? Small couplings which are not possible to detect, they also can be detected. Only thing is you have to set the delay of 50 to 500 microsecond, 200 microsecond. Remember, this is nothing but a two pulse COSY. But only thing is small delay is given after first pulse and after the second pulse. That's all. And then we are going to get the long range COSY. That means we are going to get the coupling constants which are greater than 4 to 5 bonds, which is generally weak. We don't see it. That can be detected. So this is a comparison of the COSY 90 and the delayed COSY. See some of the peaks here which are not there, you are not seeing, we are able to see it because there are small couplings here which are not resolved in the COSY. This is the delayed COSY. So correlation due to small long range couplings of less than 1 Hz or 2 Hz can be easily detected. So this is what I just wanted to tell you. I am going to stop here, but remember, with this I will finish the interpretation of COSY and discussion about the COSY. In this class what we discussed is, we took lot of examples of the analysis of the COSY spectrum, starting from simple molecule to big molecules. We analyzed, I told you what are the tricks involved in the analysis. Start with a constituent peak on a diagonal and then go into complete the square, go step by step manner, and all the connected partners you have to do. So each coupled partners is going to give rise to cross peak, which are symmetric with respect to diagonal. So you can identify all the coupled partners and make the assignment very easily. Phenyl group, what to do? If you have sugar group, sugar molecules, I told you, you have to always start with anomeric protons, which generally comes downfield. And if it is alpha and beta, depending upon beta, which has axial coupling quite larger, and alpha is axial equatorial coupling, which is much smaller. So from that you can identify which is whether the isomer is alpha or beta. That also I said. In the phenyl group, usually identify whether the singlet is there, doublet is there, triplet is there on one of the confident proton of the phenyl group, and then make the assignment, continue it in an easy way. And we also took lot of examples of big molecules to make the assignment. And of course, COSY, as I said, spectra are always recorded in the different modes, magnitude mode, phase sensitive mode, etc. But always you have to record in the phase sensitive mode, and double absorption mode is preferred for better resolution. Magnitude mode, all those things only in exceptional case where you can't do phase sensitive, otherwise it is not done. Usually you have to record the spectrum in double absorption mode to get better resolution. That is what, and I showed variations of the COSY like DQF COSY. Double quantum filter COSY gives rise to the antiphase character of both doublet and cross peak, diagonal and cross peaks, better resolution, peaks near the diagonal are not masked, get very beautiful clarity is there. And then further we can have a long range COSY or a small flip angle COSY. Small flip angle COSY gives rise to a reduced number of peaks, and the tilting of the cross peak gives you relative signs of the coupling. If you know slow direction of tilting of two cross peaks, relative signs of the coupling you can obtain. And the delayed COSY, it gives also called long range COSY, give a delay after the first pulse and after the second pulse. Then long range couplings which are smaller, this thing also get evolved. That also can be detected, gives rise to correlated peaks. So there are number of such things are there. And COSY itself, there are hundreds of experiments, lot of experiments you can do. Not hundreds, maybe that is a huge number. Several experiments like AE COSY, PE COSY, soft COSY, and small flip angle COSY, lot of things are there. Okay. So it is not possible to discuss everything, but idea is same. Each of these developed methodologies are only to improved version to get the better resolution and better way of assigning. Okay, with this I am going to stop. From next class we will start with a different experiment called toxin. Thank you very much.